and in my the services plan and the current because I am using working some data and optimization.
Okay. Okay. Yeah, I think we can start just like a small announcement about the exercise. The deadline to give the homework is at 12:15 on Fridays, every Friday. And the exercise is like, we give you extra points for the exam, but if you don't do any of the exercises, you still get the chance of getting maximum grade at the exam. All the instructions are on the Moodle page. And this afternoon, I will be publishing the solutions from last week's ones and the new ones for this week. And they're gonna be fun. So. And what else? I think that's it. So I think I want to start from something I did as last time, because it might have been, I don't know, a bit weird. So I want just to do a recap for the first half an hour today. Then we start with a new topic that is perceptrons, and we do a break at 1, and from 1 to 1:05, if that's okay for you, and then we end at 1:50. Is that all right? Okay. So last year I was showing these pictures of cubes. What I was talking about was what the McCulloch-Pitts units do with their threshold on the space of inputs. But maybe it was a bit weird to do it in 3 dimensions, and I told myself, why didn't I do the 2-dimensional case? Maybe it's obvious for somebody, but not for somebody else, so I'm just gonna do it. But basically, if you look at what I'm gonna do today and then go back to what I did last time, you see that it's the same thing, but in dimensional case. Also, as a recap of what we did last time, we saw McCulloch-Pitts units that are like these graphs where the edges can be excitatory or inhibitory. When you only use excitatory edges, we have shown that this happens. So when theta is equal to 1, this corresponds to doing x1 or x2. Am I right? You remember this? Because you or with this actually. Because you do the sum, and these are either 0 and 1. So whenever one of these two, the sum can be 2, 1, 1, 0, and 2, 1, 1 passes this threshold. So you obtain the same truth table as the OR logical function. Whereas when you do this, you have an angle because only the 2 pass. And those were the networks you could do like only using excitatory edges, where I showed as well this type of edge. What does this edge do? If it has 1 as an input, it shuts down the neuron, so the output y will be 0. Otherwise, if it has 0, it just passes 0 like the other ones. And we showed that with this type of networks, with these like excitatory edges, what you could do was only the monotonic Boolean functions. So what is a monotonic Boolean function? It's a function that given to inputs x and z, if x is smaller than z, then f of x would be smaller than f of z. And if you have ever seen monotonic functions in maths, like a function that is monotonically increasing, for example, always grows. So basically something that respects inequalities. But the problem is that x and z belong to the input space. That is something that can be like potentially weird, because it's this 0, 1 at the power of n. So what does it mean having something smaller than something else? Let us consider the case, for example, of 0, 1 at the power of 2. What are the elements of this set? Tell me if I'm saying things that are too easy, but I will try to build up upon this. But yeah, this set is the elements of containing the tuples 0, 0, 0, 1, 1, 0, and 1, 1. What does it mean putting a partial order on this set? Because I'm saying that this is smaller than this, but these guys belong to a set like this. And this is not a set where you have a total order, like the natural number. A total order means that whenever you take two elements, you can say which one is bigger than the other. And it is not the case here, because this element and this element, I don't know which one is bigger than the other. So what I do is to put what is called a partial order relation. So I have this guy that is bigger than anybody else, but then what I do is this. So I can say that this one is bigger than this because one is bigger than one. I do point-wise comparison, but I cannot do a like coordinate comparison of these two because this is bigger than this, but this is not bigger than this. So I don't know which one is bigger than the other. But so whenever I put like a line here, basically it says that I can compare those two elements. And since I don't have a line between those two, I cannot compare these two elements. But I can say that this one is bigger than this. I can say also that this one is bigger than this. Same holds for whatever power and I have. So I don't know. I can try to write you down the bigger one because I need it later. Like if I do this, I can. Sorry. So I can say that this is bigger than this and this. I can compare, not this one. I can compare this and this. I can compare this and this. And all of those are bigger than the zero vector. So this is like the same thing, but in dimension 3. I should have probably put those swapped so it was clearer, but you get the idea, right? There are some elements I can compare and some elements that are not. But if I can compare them and I know that one is more than the other, then the function, the Boolean function, should respect the inequality. Okay? This is for dimension n equal to 2. This is for dimension n equal to 3. Is this clear? Are there any questions so far? So, let me cancel the monotonicity then. So let's go. Oh, also, like these were R and N for two elements, but if I want to do for n elements, what I do is this. Is theta equal to 1. With this, I get x1 or xn, like a big or. And here I can do a big and. What should I put here as a threshold? That one? Anyway, yeah. So this is x1 and xn. Okay. But yeah, let's forget about this for a moment. Let's see. So the input space x1 and x2 belong to, in this case, to 0, 1 and the power of 2. This set is made in this way, so this is R2. But I don't care about R2, I care just about 0, 1 and the power of 2, so I get these 4 points. This is 0, this is 1, this is 1. So those are the 4 elements of this set. Do we all agree? Yes. What is the threshold doing? For the, because in this case, I draw you a plane for the case of 0, 1 and the power of 3, if you remember the last 10 minutes last time. Okay. But what is happening when it's equal to 2 with the threshold? So let's forget about this. Let's take, for example, the R between two elements, okay? What is this threshold checking is is x1 plus x2 greater or equal than beta, where beta is equal to 1. Or is less. If it's less, it outputs 0, and if it's greater, it outputs 1. So, if I consider the straight line x1 plus x2 equal to 1, is the limit from which this function changes sign, because the domain of the function R is 0, 1 and the power of 2, and it goes to 0 and 1. This machine can either output 0, either output 1. So I'm asking myself, what's the pre-image of 0 and what's the pre-image of 1? Which are the elements here? So those 4 points that are sent to 0 and those that are sent to 1. These are the conditions that checks whether something is sent to 0 or something sent to 1 is this one. And I check whether this is an inequality or inequality. So the equation of this straight line is this. Do you believe me that this equation is this straight line with slope? Do you agree? No. Yeah. So all the elements here, I don't know how to color, but yeah. These elements here, including the line, will be sent to 1, and these elements here, excluding the line, will be sent to 0. So the line is an hyperplane that divides the input space in 2 half spaces, and one half space would be sent to 1, and the other would be sent to 0. And in this case, this is the OR, but with 0, 1 and the power of 3. So the condition given by the threshold is an equation like this, but with 3 elements, x1 plus x2 plus x3 equals to 1. Because I told you that the big OR is like this. But this thing in R3 is a hyperplane. A hyperplane in R3 means a plane. When you have, like, in general, one equation of n variables, that gives you something that has dimension n minus 1. So in the case of the plane is a line, and in the case of this is a plane. And the line divides the space into 2 half spaces, and this is the same thing, 2 half spaces. All the things, I think the following slide was, yes, so like, not very well. So no, this was also the plane equal to 2. But pay attention that the plane equal to 2 does not correspond to the end, because we just said that the end was equal to n, the threshold. So the n equal to 3, threshold equal to 3 should tell you what the end does on the input space. Yes. So this was one thing. If you wanna, this is what the OR does between 2 inputs, but what the AND does. Zero, 1. So this is the OR. And here. Okay. The AND does is to check if this is true. X1 plus x2 equal to 2. This is a different straight line that crosses the x-axis and the, sorry, this is x1, x2, and this is x1 axis. Am I saying obvious things, or is this useful? I don't know. We're gonna keep going. The line is this. So only this is actually the one that outputs 0, like 1, because the rest will be outputting 0, since the line is included in what gives you true. Because the inequality greater or equal gives you the true, and the strict inequality for the false output. Because the threshold function, if you remember, was an Heaviside function, set function, something like this. This is theta, excluded, included, or something like this. So if you're greater than theta, including theta, you're true, because this is 1, this is 0. This was the Heaviside step function. That is the activation function that is placed in these machines. You've seen probably in the first week that there are different types of activation functions. In today's class, we're still going to use these things, so we're not going to make brutal changes. But so in this case, you see that like there is no other elements of the input that falls in the things that are sent to 1 except for this one that is the end because it's 1 1, right? Okay, this was just a recap, but now I'm going to do a recap exercise in which we're going to use all this. So if I can cancel, I will. Also, what is in this blackboard today is not on the slides. Because at 3 a.m. I decided that it was okay, but it is not going to go to the slide. But yep, what we're doing. So we're going to do a recap exercise that is useful because it will be helpful for you in the exercise. So pay attention. Recap exercise. Yes. Consider the function f that goes from 0, 1 to the power of 3 to 0, 1. And I can define Boolean, this is a Boolean logical function, whatever, and I can define it by telling its truth table. So where the elements are sent to be true and the others will be sent to be false. So f, I say that f, yeah. I should put more parentheses in here if I were like a very rigid mathematician, but I'm not. So I'm not going to put another parenthesis here all the time. There are mathematicians in the room. Please don't kill me. But yeah, probably should be slightly better with more parentheses, but I don't care. So I tell which guys are sent to 1 basically, and all the other elements of 0, 1 and the power of 3 that are those ones that I put here will be sent to 0. So let's do that. This is my function. And so last time I showed that proposition was proposition 2. From last time. What was it saying? You say you don't know because I didn't give you the slides. But it says that given any Boolean logical function, it exists a McCulloch-Pitts network, so made of many McCulloch-Pitts units, so these neurons that I showed you before, such that it does the job of this function. And the proof was constructive. So I was telling you how to find that McCulloch-Pitts network. The strategy was the following. So in the first layer, you put decoders for these vectors. What is a decoder? Someone remember? It's not what it is in the other neural network literature, but in this context, it means a neuron that fires only on one vector of the input space. So, for example, this one, we did this. Don't lie to me. This thing was a decoder for the vector 1, 0. Or in general, you put the rule for constructing a decoder is the following. You put for everything that should be, so for every coordinate that is 1, you put a normal arrow. For every coordinate that should be 0, you put like an inhibitory edge with the circle. And for threshold, you put the number of ones that are in the input vector. Should I write this down? I told this last time. It's on the slide. So I don't care. But yeah. We have a way of putting decoders basically. So the first layer we do just decoders, and the second layer we do an OR of all the decoders. And this like network that is just 2 layers, the proposition was saying you need a network of just 2 layers to do the job. Basically. But yeah, this is a strategy that finds you a network. The question that I'm going to try to treat this time is, because last time I told you that this proof wasn't given necessarily. It was giving you a network that does the job, but it doesn't tell you if it's the minimal one with the minimal amount of neurons. Can we do better? We don't know. And I'm going to show you today that it's not. We can do better. Like once we find a network for But this is like, let's say, this proof gives you a strategy for whatever function you have to give you a network that does what the function is doing. Okay. Do you wanna try to do this on your own, or while I cancel? It's not hard. We should just put in the first layer decoders for these vectors and then put an arrow of all of them. So I told a decoder for any of those, so I need at least 3 ones, and in the end an OR. I told you before that this was an OR of 3 elements, so this is not shocking. Decoders, I'm just explaining those, but basically this vector has all ones, so I put, sorry, smaller. And I put theta equal to 3 because it has 3 ones. For this one, I put theta equal to 2 because it has 2 ones, and for this I put again theta equal to 3 because it has 2 ones. And then I put normal arrows for the first 2 and the weird arrow for the third one. Today's class is not about weird arrows. We're gonna drop that very fastly, thank God. So this is what we're gonna do. And here we put weird arrow here, normal arrow, normal arrow. And this is the network that does this function. How can we prove that this is the right network? We do the truth table of everything that's happening. How many of you want me to do the truth table of this thing? You don't? Like, how many for the yes? Oh my God.
I want.
You want the truth table? No one? I don't do it? You believe me that this thing does that function? On the exercise sheet, I want you to do the truth table. Because it's not clear whether this works or not. But yeah, okay, let's not do the truth table. So the question is, can we do a better network than this one? Because this is the one that the proof gives us without thinking. We just apply the constructive proof of this proposition. Can we do a better network? Can someone do a better network than this? Like a better meaning with less nodes. Now you want me to do the truth table. The truth table wouldn't have helped you. Also, to write the truth table for these kind of things properly, you have to give names to this, like the sum for this, the output for this. I don't know, you put S1, Y1, you call this Y, or like you calculate the sum for this, Y2. And whenever this thing shuts down, you put a little bar on the S. So the neuron has to be shut down because this is 1 for some cases, etc. This is S3, Y3. You calculate the sum and then you calculate the output of this particular neuron. And the truth table is gigantic, but yeah. So I gave you 5 minutes ago the definition of monotonic. Is this function monotonic or not? Monotonic means 3, it's nice with respect to the inequalities. If something is smaller, it becomes smaller in the output. How many for yes? And how many for no? For no? Oh my God. I'll let you think about it a little bit more then. So the people that didn't like make a choice now can choose. Why do some people think that this is not monotonic? How do you prove that something is not monotonic?
because there are points, arrows that can break the monotonicity.
Yes. So can you show me if it's not monotonic? Can you show me a point that breaks monotonicity? So something that is smaller than something else, but the image is the inverse. You have to show like a vector of these that breaks monotonicity, basically.
No, like I was thinking because there are immediate arrows
Yes.
that it could break monotonicity. Because I remember there was a kind of example
Yes.
that you were expressing this.
Yes. So last time proposition 1 was saying that all the monotonic functions can be written with a network that is only with these edges. But if this was monotonic, every function can be written with different networks, actually. But this proposition was telling you there is a network that has only these edges that can express that function.
There is also a comment that says that it's not monotonic. Just saying.
Someone in the chat? Can you say why? In which point monotonicity is broken? Basically, what I want to say is that this proposition doesn't help because I could be able to write a smaller network with this, and then it would mean that is monotonic actually. So if you actually find a network that has only these to do the same job, then you've proven that it's monotonic. Like it exists a network that does that. Or if it's not monotonic, then show me a point where monotonicity is broken. So one vector of this, B, one of those belonging to 0 and 1 at the power of 3, such that for two vectors, sorry, W and V. Now let's not use W, Z and V, such that Z is less or equal than V, but F of Z, for example, is greater than V. Imagine this is 1 and this is 0. So there is something smaller than something else, but the image is on the other side.
Can I give a hint that it's more?
What do you think it is of the two?
Whether it's monotonic or not?
Yes, do you think it's monotonic?
Yeah.
So someone else thinks it's monotonic too. You change your mind.
Yeah, I mean,
One can also try with every point.
yeah,
And see it
initially
doesn't.
I just, without thinking that much, I just saw the inhibitory type, and then I thought, of course, it should be non-monotonic because I just quickly thought. But then I compare each of these and
Yes,
then I
like if you do the computations for all these, you will not find the counterexample. Like if you try all the, we can do it actually. If I apply F to all this graph, I apply F. The numbers that I obtain are these 1, 1, 2, 1, 0, 0, yes, and all the rest is 0. Right? So this is bigger than this, but this is greater or equal, so it's fine. This is bigger than this. There is never a 1 down a 0 somehow. That's what breaks monotonicity. What did I do? So monotonicity would be broken if I had a 1 in one of those edges, a 1 down and a 0 up. Because up should be bigger, but then the image is not. So proposition from last time anyway, since it's monotonic, tells us it exists a network with only excitatory edges, called it uninhibited network. I don't even know how to write this. That is equivalent, so that has the same truth table. Let's find out what that is. So no inhibitory edges.
How's the sponge? Does it need more water?
Probably yes. Anybody? I think you can do this one. If it's too stupid, it's just the beginning of the class. Then we are just gonna do more stupid things. No, it's not true. What do I count? So this. I think there might be also different ways of doing that. Should I do it or someone has ideas?
Just keep in mind that 30 minutes have passed.
Really? Oh God.
Yeah.
Then I will do it. Or someone has ideas very quick. I don't know if you look at these conditions, you can think about the logical whatever ways of expressing the same thing. Like these two guys are telling me that they want both x1 and x2 and I don't care about x3. Whereas when I look at these two, the first and the third, I want x2 and x3 and I don't care what happens to x1. So I can say that f of x1, x2, x3, intuitively it seems to me that it is x1 and x2 or x2 and x3. To verify that is true, should write the truth table for all this and then see that it's actually make sure. But if you write the truth table, it's true. But the idea is really that these two and these two put them in order. If you write the truth table, so the truth table of the end, the truth table of this end, and then you, and the truth table is big because all the elements in the inputs are like all the inputs. But yeah. And so having this, we can write the network because it's and or, and I taught you how to do that. So if I take x1, x2, and x3. Yes. I'm doing x1 and x2. It's an and between two elements. And this is an and between other two elements. And then I do the or. That is an or between two elements. So I do or. No, the threshold of the or is always 1. Then again, you can write the truth table from this network and see that it's the same as this. This is this. So you see that proposition 1, 2, whatever, 1 is giving us kind of, but since this was monotonic, kind of a smaller network with smaller, less edges and less nodes. And this was doable actually just because we had very few variables, like we found a trick. Whereas the proposition was giving whatever big network you have, you put decoders in the first one, you put OR, and it will work. It will be probably uglier. But you see that in some cases it's possible to simplify. And in this case, we can simplify and use only excitatory edges. So this is something that I just said last time, but I wanted to show you an example of the fact that they're different, but they do the same thing. Are there any questions so far?
I have a question.
Yeah.
So you have the f with the three variables is equal to some logical sentence.
Yeah.
So how did you came up with? Is that the normal form thing or what's?
Yes,
What-
probably it is the normal form I was mentioning last time.
Okay.
One should, there are some things to check, like some weird cases, so I don't remember exactly, but might be that. Yeah. But the normal form might contain not as well inside. So it's not that the normal form is always just ands and ons.
Okay.
So that's probably you can write. I think the normal form that I was mentioning last time gives you a different network here.
Okay.
But if the function is not monotonic, I think you can still compute the normal form. And you get something else. Yes. But in this particular case, probably if this is the normal form, it has this shape just also because you can do it only, it's monotonic, so you can do it. You should be able to do it in this way. The good thing about this proposition is that it like guarantees that you have only two layers. So like it kind of bounds the number of layers that you can have. Yeah. So if there are no other questions about McCulloch-Pitts units. Nope. Yeah. We should go on then and see the rest of the thing. So McCulloch-Pitts units were the first like model of a neuron, a computational mathematical model for a neuron, because one of those guys was a neuroscientist and the other guy was a guy who did logic. Were there questions online?
No.
And so I showed with this proposition that you can do all the Boolean functions with this type of networks, and with using both the edges. If you use just one type, you can just do monotonic Boolean functions. So this is the class of functions that these machines can compute. And this is good, but maybe it's not enough for some reasons. First of all, there are no weights. So the arrows always pass the input or shut down the neuron in the case of this type of arrows. But there is no flexibility in some sense in how the signal is passed. You cannot like give importance somehow to some inputs more than the others. Like the input either passes, either everything is shut down. So it's kind of a rigid model in some sense. So there are in another way, probably this talks more to the computer scientists, I don't know, there are no free parameters to adjust in order to make a network like this adapt to, like I say, a particular problem. They're very rigid in some sense. You fix the threshold, you fix the arrows, and the machine goes without like being able to optimize it in any ways. And so before solving a problem, you need to write your network fully. There is no liberty in that sense. So what people did after was to introduce perceptrons, so to introduce weights. I told also, I wanted to recap before this thing about the hyperplanes and the straight lines, because as I showed you before, the straight lines that were defining what was mapped into 1 and what was mapped into 0 were all of this type, for example, x2, x3 equal to some variable, to some threshold, okay? And they were dividing the space into two halves. But the fact of having coefficients ones here in front of the variables is due to the fact that the weights are ones, okay? So in some sense, all the lines here are all parallel. I know they're all like, as you saw, like in the and the or, either they were planes stuck in the same direction parallel, and the height where they were stuck was determined by this theta that was belonging to the natural numbers. So there is no flexibility in how one divides somehow the input space, okay? And perceptrons were introduced to add flexibility and to make these models more sophisticated, adding weights. Probably you've already seen weights in the first week somehow. So this is the guy you introduced, what is called the classical perceptron in 1957, that is Frank Rosenblatt. And in the 60s, some other guys tried to also work on perceptrons, and actually what goes by the name of perceptron is what means can happen. If you are looking for historical remarks on anything like that, in the Rojas book, at the end of every chapter, there is a page of historical fun facts. So if you like this kind of readings, you can have a look at that. So this is the original Rosenblatt's theory, like model, and it comes from the fact that what he wanted to do was to create something that is more close to vision in some sense. So that's why it calls this retina. So the retina is what the hits the back of your eyes in some sense, and then wanted to create something that does what the brain does to signal coming to the retina. I don't know if you've worked with vision or like read vision science papers, but it's very clear that what hits the retina, it's not what we see. Like there is something that is happening. It's not that we see something that is objective there. Like the brain is doing some stuff on the signal that hits the retina. So what he wanted to do, it was like create a model for that in some sense. And this model needs flexibilities because the visual system gives importance to things and not others. I don't know if you've ever seen, there is many like fun facts about vision. I don't know, this like visual illusion. Like I worked for like, I'm still working on color perception. So color is not something that is fully specified by the physical similar of to what hits the retina, but like there's a full of like it's a complex phenomenon in some sense. So if you have, I don't know if you ever seen this. This thing was discovered by Chevreul, a French chemist or whatever. If I color this gray and I color this gray, it's called simultaneous contrast. And I put here like a light background and here a dark background, you won't perceive the same gray as being the same. So the brain is doing something related to the context. So that modifies the way you're perceiving the same things into two different contexts. So that's the idea. So that's why at the beginning he talks about local connections that he says they are deterministic. So whatever is hitting the retina is transferred to some model, like some picture, for example, or some pixels, I don't know. And then on that, you apply, this is the input of your network. So from here on, that is called projection area. So we have this square with like what hits the retina. And then we have like connections. And these connections are, he says stochastic, means that are like determined probabilistically, they change. And what does it mean change? Like putting weights and being able to adjust them. If you are trying to model this phenomenon that is weird, like it's not clear how it works. And this was like at the very early stage, this was like Rosenblatt, like model. In other words, what he did was, he used this a lot for this, what is it called? Pattern recognition problem. So you have something and you have to recognize that this is an output, something like that. And you also talked about like locality. So this is the projection image. So what is like done after the retina in some sense. And in this projection image, he defines what he calls the predicates that are some kind of like nodes that have a receptive field. That is something that was discovered probably after, I don't remember correctly, but like in the meantime, while these models were developed, there were also biologists who were doing like the actual like biological counterpart of this. And so those things that were model computationally had actually some kind of like actual thing that happens in the retina. And so what this model does was that every predicate P1, Pn, etc., has a certain region of attention or whatever that is called the receptive field, and the predicate can input output 1 or 0, and gives that to the rest of them, with weights to the rest of them. So now, since I don't want to do biology weird thing, let's go back to math. And we're gonna define what is a perceptron. And that is not something particularly crazy because it's something that is kind of the same thing I did last time, but with weights. So first thing is that we forget about these inhibitory edges. We just have normal excitatory edges with weights. So we said that we call this a simple perceptron, so like one computing unit. Maybe I can do it. I thought that we should have had a pause now.
Yeah, it's 1 o'clock.
Let's have a break while I come. Yeah, 5 minutes. Deadline. Since someone didn't hear about this 12:15 thing, the deadline is today at midnight. So I will be always at midnight. So new announcement Friday. This week. Let's do this. That's what the current was, right? Yeah, but that we're gonna see something very soon. Yeah, so what is a perceptron? We forget about this. We just use this. So we take inputs. Let's do a table, maybe, for what we were doing before and what we're doing now. So a typical perceptron is a computed unit with threshold data, meaning that the activation function at the level of the neuron is the Heaviside function. So the Heaviside, the activation function is the same, except or whatever activate. Which when it received an real input x1 xn, the wedges with the associated weights, blah blah blah, output 1 if the inequality holds, otherwise it outputs 0. So this means that it does the sum like we did with the ands and the ors, but it adds weights because before we had weights 1. And this is like the Heaviside function definition of the sum. So like you basically, okay, this was the Heaviside activation function. And so what it does is to do the Heaviside activation function of the sum. No one is scared by this sum. Like, have you seen that in other contexts? Okay. 1 and WE. W's are weights, that's why I tried not to put it in other conditions before. If I did, I'm sorry. Weights are always W's. This is the output. Why? So now that I did this, why? Before. Let's talk about where we pick the things. Those are the x sides. Before they were belonging to 0, 1 to the power of n. Now they can be real. Because it says they can be real. Or whatever input you want. I mean, this is a subset of this. So if you want to do Boolean functions with perceptrons, you can. That's what today is about. But and weights. Weights. So this is a table. Weights were all ones here, except the inhibitory edge, but still that. And here they're real again. It's a vector in R of weights. Yeah, this is WE. I should put this. I mean, you understand. To this. The threshold, again, now it's real. Can be anything. Before it was N. And anyways, the output though, why? Because the output of the neuron one. I'm gonna do a drawing of the neuron. Maybe I already did. Yes, this is a neuron with two things, like a perceptron with two things. So the drawings look the same, but we have tiny W's. But the output Y is still in 0 and 1. Okay, nothing crazy, just this. What else? No inhibitory edges anymore. The output is the same. Yes, that's what I said. All good? Yes. And this is we just put the threshold and we say what it is. Yes. Okay. So we consider an example that is this one. We put weights 0.9 and 2. and the threshold equal to 1, the input becomes x1 and x2, can belong to R or whatever, and you check whether the sum is greater than 1 or is less than 1. So it's either 1 or 0. So the question is, what happens to the input space now? Remember the very first thing I did today, the one with the, I made these drawings at the beginning. And I made this, oh, this is the order, and this is the end. Remember this? What happens now? Anybody? So the perceptron basically does something to the input space in the same way as McCulloch-Pitts units with excitatory edges did to the input space. So the idea is that the input space is this kind of projection of the retina, some kind of image created on the retina, and the function is trying to guess something on that space. So it's trying to say, oh, this is 1 and this is 2, like these points in the retina, like trying to do something on this image. Trying to divide it into 2 parts, right? Anybody? So before I told that the straight line that was dividing the input space, depending on the output of the neuron, was determined by the threshold function. But the condition that is verified here is this one, right? Either is greater than 1, either is smaller than 1, because the threshold is 1. But this is a straight line in the plane x1, x2. But well before we had all straight lines that were of this type. Or greater, smaller. We had to check what this is and then divide. The greater was enough space for us. So, in this case, I have x1, x2, that is my input space, that is R2. That I told you just now that we use whatever we want as input. And verifying this condition, if this condition is greater than 1, we go 1, otherwise no. So basically what we do is to trace the straight lines that has this equation. In this case, 0.9 x1 plus 2x2 equals 1. This is a line in the plane again. But these lines have many degrees of freedom that are determined by the weights. Now I'm gonna draw the wrong straight line. We need to do this. I don't think this is this one. But so all the points that belong to this straight line and that are up will output 1, and the rest will output 0. I don't think this straight line is this one, don't believe me. But yeah, and I don't think it's that one. I know, maybe yes, that one might be the correct one. So, no, this one was kind of colored the upper part on the screen, and on the slides you see the contrast. But yeah, the upper part, including the line, will be mapped to 1, and the lower part will be mapped to 0. So you see that these type of machines are more powerful than the ones we saw in last class, because they have more, like, however I change the, so the condition I'm verifying is always this one. Okay, let's make it what's here. W1 x1 plus W2 x2 equals to theta. This line determines how I split the input space, what I'm saying about the input space with this function, okay? But these ones, I can move them. That's the whole thing about machine learning. I can like learn those parameters. And these also, I can set them. I could set them also before, but yeah. So the idea is that I have more degrees of freedom. I move my weights and I will change what the function does on the input. Whereas before I couldn't do that. This is the idea. Okay. And I said, okay, it's separate. The input space 2 is separated with the pre-images from 0 and 1. Is this clear? Pre-images means what the function associated to the neuron sends to 1. What the function. If I associate to this perceptron a function x, we consider like, yes, that y is f of x, y for x1, x2, for example. There exists a function that is modeled by this neuron, that's y gets the output. Then I'm considering f minus the set of all x1 and x2 such that f at the -1, yes, of 0 is equal to this one. I'm considering just the set f -1 of 0. That is a subset of R3. And again, I'm considering f -1 of 1, that is a subset of R2. F -1 of 0 is the set of all the x1, x2, such that f x1, x2 equals to 0. Same thing holds for 1. That's what pretty much means. What is sent to 0. The set of all points that is sent by f to 0. And this function is clearly not bijective because it's going from R2 to a set with just 0 and 1. So many things are set to the same thing. So it's not that when I come back, I will necessarily find just one point. I can find. That's why those are sets. Yep. What is this? Is everything good so far? So we've seen last time, sometimes for some examples I put theta equal to 0. I think for the NOR operator, we did an example like this. I know that, 0 belongs to the natural number. Some mathematicians will tell you no, but actually for most of the mathematicians it's yes. So you can set, since theta belongs to n, we can set theta can be 0. And it was 0 in this example, so we had done this example last time. No, sorry. Okay. I think this was the NOR function. Somebody remembered. Somebody replied when I asked to the class which was this one, and someone replied no. So we did that. So theta can be 0. Why it's nice to have theta be 0? Because then when we do the check of the what's the sign of the sum, we do this check every time. We do this check here. Sum, right, that goes from 1 to n of wi xi. We ask whether this is greater or equal to theta to decide what the output, okay? But if theta is 0, I'm just checking if something is positive, so it's cooler. There's other reason why we like theta is equal to 0. When we have theta, for example, in the case of a straight line, W2 equals to theta, this line doesn't pass for the origin. If theta is different than 0, do you agree that when theta is 0, all these lines pass through the origin? Same for the hyperplanes. So in the general case, whenever you have something that has equation this, this is an hyperplane, but it doesn't pass from the origin if this is not 0. So it's cooler to deal with the hyperplanes that go through the origin.
Nicoletta, is that the NOR really?
What?
Is it really the NOR that?
I don't remember, but I think yes, we did that. I think that's on the book.
But like in all cases, it's gonna be 0 and unless it's 0, 0. Right? Because if it's 1, it's gonna inhibit in both cases. So there's gonna be inhibit, 0, 0.
Yes, that's what the book says.
Hmm?
You have to do the truth table. I see. I think the NOR is that, no? I don't know.
Oh, okay. I'm wrong.
Yeah, we did it last week. That's one.
So, and also there is another thing. we want to adjust the weights to move our lines and to fit our problems. Imagine that we have I'm gonna do that at the end of the class. Imagine that we have two clouds of points and I want to separate them, okay? I want to adjust the line in order to be split in the two lines. Adjust the line means learn the weights that split the points. That's the goal. But I want to do this with this machine, so that's why I'm taking my time. I'm sorry if it's too slow or easy. I don't know. What's your background as well? It's a bit difficult because if you come from maths, you will like some parts of this and hate others. But if you come from computer science and deep learning, you might do the opposite. So there is no intersection kind of. But let's see, maybe we can do it. But yeah, the thing is that when we put the thresholds on the nodes, the thresholds are fixed. Like in the McCulloch-Pitts unit, I specify my network and then I let it run. There is nothing I can do. And I would like to put the threshold together with the weights. So whenever I adjust my weights, I adjust also the thresholds. So I can do one thing for all of them. And I kind of can do that by doing this. This is called an extended. What is called this? It's called an extended input vector. So basically, I take the threshold and I make another input vector. Why do I do that? Let's okay. Let's take it. It's the same when it's minor, okay? What I do is crazy math, so I take this and I bring on the other side. I from 1 to n, wi xi minus theta. And so I can check whether it's greater or equal to 0 or 0. Same for the minus. But so what do I do with this? I say, oh, okay. Minus theta is the weight, and I call it weight n plus n. And 1 times 1 is another input vector. And that's it. So I treat the threshold as we call it bias. Some people call it offset. It's a translation. Yes. And that's it. So we add another extra thing, and the input is always 1, and the weight is minus theta, because I said that the weights belong to R, so I can do whatever I want, it can be negative, I don't care. And here I just check for the sign of this thing. So the new input vector is this with a 1, and people who like projective geometry might see something here. Like this extended, like you find something here. Oh, yeah. But can be something for some people, okay? But it's not really important. But here the weight vector is this, and the last vector is the threshold that I adjust. I don't even call it threshold, it's like just an extra weight. You probably have already seen it, so it's not really crazy. But yeah. Okay, how much time do I have? Okay. So we have seen that all the McCulloch-Pitts units can do the Boolean functions. Can those things that are more sophisticated do the same or do this better? Because those are more sophisticated. I told you that you can move the straight line in a very more fine way. Like the input space, you can really move the line by adjusting the weights, okay? Whereas before we adjust lines like this with fixed slope. Can we do this? So we say that the question, the proper question is, a Boolean function is computable with a single perceptron, because before I was saying, oh, the Boolean functions, I can do it with 2 layers. If you try, probably you can try it during the exercises, to use McCulloch-Pitts units, but just with 1 unit. Like you have 4 options. No, you have the 4 option times all the possible thresholds, but there is not so many. So McCulloch-Pitts units with just 1 neuron don't do much. So we did that. We could do last time proposition 1. We could do all the Boolean functions with the 2 layers of McCulloch-Pitts units. The question is now, can we do the same thing but with just 1 perceptron? Let's find out. Before the first question is how many Boolean functions do we have? From 0, 1 squared to 0, 1. I made you the same question last time with n. And you replied, so you can reply this. Anybody? It's like the functions that go from, it's like the or, the and, etc., and all their brothers and sisters. Yes. Yes, because last time we did the possible outputs that you can have. Yeah. And last time we saw that for n, it was 2 to the power of 2 to the power of n, right? So if we put n equal to 2, you obtain 16. So, and if you can recognize between these brothers and sisters, you can recognize F14 is the OR, F8 is the N, and Fx is the XOR. So, I'm not gonna do it with all of them, but I wanna just show you some examples. Let's just consider these three that are the same. Oh God, did I do this? Yes. Okay. So this is just the definition of what is a perceptron computable function. So a function that can be computed with a perceptron, but it's just like a straightforward conclusion of the definition of what a perceptron is. So a perceptron computable function is one that the points that in which the function gets 0 can be separated with a straight line from the points that where the function gets 1. So if I can find a straight line, I can find the weights. And I can find also the straight line is specified also by the theta, because I don't want all. Depends on how I write the problem. Imagine that I write without the bias. Let's forget about the bias, okay? Imagine that I have the network with the threshold, whatever. The threshold and the weights specify where this straight line is placed, okay? So if I can say that a function, if I can specify this line, and I know what's the image of the function, that can be just 0 and 1, because I told you that perceptron's output as McCulloch-Pitts unit 0 and 1. Like the domain is more complicated, like R with all these like lines, etc., the weights that we added, but the output is still 0 and 1. So if I can find a line that tells me that separates where the function is 0 and when the function is 1, I can write a perceptron and does the job. Okay? And we define this as perceptron computable. Again, this was kind of colored, but apparently it's not. So let's consider these functions. So I just took the famous one. You can do with all of them. Actually, one exercise is one other, of course. But yeah. So is it clear the way I depicted this? So the input space, I said that it would be R. But in this case, we're taking, since we want to compute the Boolean function, the domain is still 0, 1 to the power of n. But the weights belong to R. So let's put it this way, x belongs to 0, 1 to the power of n, because the functions that I want to compute are Boolean functions. And this is right. And yeah, but the weights can be anything. They belong to R. And the theta belongs to R. Okay. Although I don't know if it's like a weird notation, but basically let's put this way. Consider 0. So okay, this is the vector 0, 0, this is the vector 1, 0, x1, x2, 0, 1, 1, 1. Okay. And I put 1 if the function sends it to 1, because the OR sends to 1 all these vectors, right? We could also use a different notation. I don't know, use crosses where it's sent to 0 and circles where it's sent to 1. So this is the OR. I don't know. I hope this notation is fine. The numbers on the edges mean where the function is sent. What is the image of those points when you apply your function? Or when you apply the AND function, because just 1, 1 is sent to true. And when you apply the XOR function, so only 1 and 1, right? Exclusive OR as this truth table. right? I just want either x1 or either x2. I don't want both. I don't want none. So which ones of these functions are perceptron computable? For example, is the OR a perceptron computable? Yes. Why? What you just said means being perceptron computable. I put yes, I do have that. There was one.
You can put line there, like nice. This line.
Yes, like this. This line works. There is actually many lines that we could use. So there is actually many perceptron that we use because we have that's that kind of the power of this model. That like whatever line you take like this, I don't know, would do the job. Even the one that passes through them actually. Because it includes this in the truth. And all those lines that split those will give you a perceptron that works. Okay? There is many. And now about the end. So this also like to do this, like there is this graphical depiction, but you can also write a perceptron. So I don't know, you choose a line, you take the parameters, and you say, oh, the perceptron that is done in this way. I take the parameters of this line R. I don't know what they are, but let's say that there are two weights, there are two numbers. I put those two numbers as weights. I put the offset as a threshold, and then I say this perceptron does the job. Actually, there's a family of perceptron that does the job. That's what I with it. Okay, let's consider this. How many people think the AND is not perceptron computable? How many people think it is? So, this is the AND. So if I do this, I'm fine. If I do like the McCulloch-Pitts unit, like, and I pass through this, I'm also fine. Like all these lines do well. This line does not do well. Okay. Like there's a region of the plane that works fine. Whatever line I pick there, I'm fine. I can write a perceptron, I can write many. How about the XOR? Nope. So yeah, this is just what I just said about the AND and the OR. Let's consider the XOR. So, okay. Saying that I cannot find a line that does the job is not really a mathematical proof. So if you suspect that this thing is not perceptron computable, you have to prove it. Like there is no fate or no like there is no, the intuition is clear, like think to everybody. How do I even write like a line that does that? How do I write it? Like if I put horizontal, nothing works. Okay. But yeah, let me prove it then. So we have to prove it by contradiction. We imagine that it exists a perceptron that does the job, and we show that it leads to something that is contradictory. Okay. Let's do this. I imagine it exists a perceptron that is done in this way. So I have x1 and x2. I have weights W1 and W2. I have threshold theta, and I have output 1. Okay? And I suppose that y is x1 XOR. I don't know, some people do also v with the circle, is that true? I think in the exercise sheet we put this. I don't know, whatever is fine. But yeah, I suppose this is true. So how the perceptron computes these equations, right? The perceptron outputs 1 if this equation is greater than theta, and 0 if it is smaller than theta. So when I say I suppose it exists a perceptron, I say it exists the triplet W1, W2, theta. So it exists alone. Okay. So, and I'm sorry, I have to write at least one truth table today. That is the truth table that goes x1, x2. Maybe I have to reflect the book. So, okay. I don't like it. Yes. For each of these inputs, I do this. I evaluate the sum. Oh God. Okay. So, what does the sum for each of the inputs? I evaluate the sum W1 x1 plus W2 x2, and I write the value here. I call this column sum. Okay, like we did in McCulloch-Pitts here, just with weights. The sum here is 0. Do you agree? I tell you again, W, W, and theta parameters. So whenever I have a W, I just read W, theta. What is this? W1. This is W2. And this is W1 plus W2. Okay. If this is true, okay, yeah. I have to cancel this, I'm sorry. Just you have it there. So this is x1 XOR x2. What is the truth table of this? 0, 1, 1, 0. Okay. If this corresponds to the output of the perceptron, so if this is true that this is equal to y, the output of the perceptron is the fact that this 0 was smaller than beta. Because it outputed, like I output 0 whenever this is smaller than beta. So if the output was 0, then this was smaller than theta. If the output was 1, means W1 was greater or equal than theta. Same for this one. The output was 1, so W2 was greater or equal than theta. And this is W1 plus W2. If the output was 0, means that this was smaller than the threshold, didn't pass. Okay. My goal, since the intuition is that this is not perceptron computable, is that some of these conditions that come from assuming that this thing was perceptron computable are contradictory. Can you see that they are contradictory? Yes. Because if I take these two, okay, this first condition says, okay, this is 0 and theta is here, theta is positive. I need it. And these two say that together, say that W1 plus W2 is greater than 2 theta. But if theta was negative, it could be fine, you know, because this says it's smaller than theta. Imagine that theta was negative. And this is like 2 theta. Because theta was negative. That is not. But if it was negative, those two conditions wouldn't be contradictory. Because if I say, it's greater than 2 theta and smaller than theta, I'm fine, I'm here. Right? But it's not. Like, so theta is positive. This is 0, this is theta, this is 2 theta. And this one is telling me that I'm greater than 2 theta, so I'm here. But this one is telling me that I'm smaller than theta, so I'm here. Where I am, like where is this contradiction? When we finish, we do this, or we do a square when we finish a proof, and we're happy about it. Are there any questions? Did I go too slow or too fast? How many for too slow? How many for too fast? Can I go back to something else? Or do through all the lecture? In this one? Yeah, so These two conditions, do you agree that give you the, until this table, is it clear? No?
Yeah, this is clear, but that last part was.
Okay, so if you agree that these two conditions lead to this, right? Because I do the sum and the inequality is preserved. If both of them are greater than theta, the sum would be greater than 2 theta, because each of them is greater than theta. Okay, so the sum is greater than 2 theta. But this condition tells me that the sum is also greater than, is also smaller than theta. Okay. You can see it also in this way. If theta, since theta is this condition here combined with this tells me that this is greater than 0, like the sum is positive, okay? Like the sum cannot be greater than 2 theta, and at the same time, sorry, forget about this. Let's consider just those two things. The sum cannot be greater than 2 theta and smaller than theta if theta is positive. Because if theta is positive, imagine that theta is 1. And so 2 theta is 2. The sum, that is one real number, because these are two parameters, but are two like real numbers. So you do the sum, and either you stay here, either you stay here, but you cannot stay on both sides at the same time. You cannot be smaller than theta, so belong to here, and belong to here at the same time. It could work if it was negative, because it would give you an interval where you can pick your sum. But in this case, it gives you contradictory. I put it also on the slides. If you want, we can talk about it. So this is the proof. Just what I just said, but like written nicely. Yes. Well, yes. So what the XOR taught us, and how can we generalize this? Because I did this with 2 variables, can we do it? And that's always the question. We have to propose a concept that if a set of inputs is linearly separable or not. Because the problem of the XOR is that we could not separate those 2 ones from those 2 zeros, right? We couldn't find a line. This contradictory result tells us that it does not exist a triplet that does what I want. It does not exist theta, W1 and W2, such that there is a line. So means there is no line that can separate. The intuitive thing that you got from just the picture was clear, like there is no line that can do that. This is just a proof that the line does not exist. So can we generalize it? Say there is, for example, in R3, there is not a plane that can split my input. So I want to introduce a concept that tells you, given 2 sets, whether there exists something that splits them into, like in R3, it's like a plane that splits into half spaces, or in general, we say that there is an hyperplane, so something that if you're in dimension n, has dimension n minus 1. So if you are in R4, it is something that has dimension 3, etc. But we don't care. It's just something that is specified by a linear equation. So we call it linear separability because it means that it exists, the analog in n dimension of a line that separates the set of 2 points into. Separates with like containing in one part the line. Like you see that one of the 2 inequalities was with the equal. Okay, so a set of the points can be on the line, let's say. And it is the set of A. So we said that 2 sets of points A and B in an n-dimensional space, we are linearly separable if it exists n plus 1 linear variables, because you see that here we were in 2, but we were looking for 3 variables, W1, W2, and theta. The line is specified by like the direction and the offset. Okay. And n plus 1 real numbers, so these are the weights. Wn plus 1 is the theta. Or just we call it Wn plus 1 because we want to treat the threshold as a weight. So if you like whenever we are actually using machine learning, you just throw that, put the thresholds to zero and you throw that at the things that you're optimizing. And so such that for all the points that belong to one set, they satisfy the equality weight of greater or equal. I just put Wn plus 1 instead of theta. And here the other one is it's strict 1. Okay. Just like the n-dimensional version of what we did for dimension 2. So the idea is that a perceptron, a general perceptron, so that with n inputs, can only compute linearly separable functions. So again, if you find these weights and the threshold, you can write a perceptron and that's the job. So if I have a function that satisfies this property so that I can linearly separate them, I can write a perceptron, at least one. I can write many, as you can see. So again, we consider now the Boolean functions from n to 0, 1. We said last time how many of those are there, 2 at the power of 2 of n. Because before I showed you the 16, let's say, where n equal to 2. But imagine that you have n, it is 2. The question is, even just for the Boolean one, because I wanted to show what kind of perceptron compute for inside the set of the Boolean function with just one perceptor, how many of these are linearly separable? Because if it's all of them, it's easy. Like there is one perceptron that does the job. But it's not all of them, because for the case n equal to 2, we learned the lesson with XOR, that is not true. That one I cannot compute it with a perceptron. So those models are like more sophisticated, but with the Boolean function they fail, even with n equal to 2. So there is a question like how many functions can I actually compute and how many I cannot. So someone can reply to this question? Have any idea? I don't know what to do with these questions. I will stop the next. But yeah, okay. So for the case n equal to 2, there are 14 that can be done and 2 that cannot be done. For n equal to 3, there is that number and that number. So the total is 256, and the one that you can do is 104, and again for n equal to 2, but people don't know. So that's the situation. Like there is research going on, there is upper bounds on the sets that you can compute, but it's like still like a weird question. I don't even know why did they put that as a question. But yeah. So there is another concept, because okay, I'm gonna do this next time probably, but like I wanted to show you an algorithm that like updates the weight and finds if they are separable, if the function is linearly separable, then I can cut it and I can find this separation, and so I can find a perceptron that models that function. So that tells you the inputs. Imagine that you have two clouds of points. You are able to find the hyperplane that cuts them in two and says so the one set is down and one set is up. And so you have a perceptron that tells you 1 on one set and 0 on the other. So you have a perceptron that recognizes those two sets. And it does updating the weights, but you have to do an assumption on those sets. And an assumption so on the function that's which points belong to which set. And we're going to prove it like by using the tools that I just said, but it's next time's topic. But so the idea is that we have to introduce actually like a stronger hypothesis that is not so strong, but yeah. We have to talk about absolute linear separability, which is almost like linear separability, but I cannot touch with my line the points. Okay? So the points that are true in the output is not greater or equal, it's just greater. That's the same definition as before, but there is a great instead of great equal there. Also, this is true when the input is in R2, but if the input is finite points, those two notions are kind of this. I can always find, given like if the set are finite points and I have a line that touches some of them, if I move it a little bit and doesn't touch them, it's fine. So if you have two finite sets A and B, if I have the hypothesis that the sets are finite in an n-dimensional space that are linearly separable, so I can find a hyperplane of a line that touches some of them and a set that separates them, then they are also absolutely linearly separable. So the proof is that I move the line a little bit. There is an actual proof on the row just if you want to have a look at that. But basically, if the set of points is finite, I'm fine. Like absolutely linear separable or linearly separable is fine. I just move it and with the line since I have the liberty of moving the line over the real number. So I have like high precision. So what we're gonna prove to next time is this. So we have 2 points. I called some of those positive and some of points negative. I assume they are like absolutely linearly separable, the definition I just gave you. And then I have an algorithm that starting from a random set of weights finds the weights such that the hyperplane corresponding to those weights splits the percentage. And this is the algorithm that we do next. So that's all I think for today. Are there any questions? You can always email or like whatever. I give you the slides. The slides are already online, so, and I'm gonna try to put them before the class, so everything is gonna be fine. And the deadline for the exercise is exactly now.
We'll update that in the Moodle. Yeah.
I publish the exercise for this week this afternoon. That will be about this. McCulloch-Pitts and Prencipe. Not about this. Not about this last one, but about what we did this week. It's gonna be fun.
And with the updated deadline, the solutions to the previous exercise will come like the day after, so Saturday.
Contact grades along the semester or only at the end? You would give grade
At the end, usually.
I mean, for the exercise, it's, I don't know. Yeah.
I mean, the grading is going to happen as soon as possible after the submissions are done, but you're just going to see your grade.
I like all the information about the point from the Moodle. We wrote like there's also the option like you don't do any of the exercise and you get some perfect and it's fine, or you do half exercise and lack of it. It's really technical calculation. We wrote like there is also different with
Bye, guys.
Were there questions?